Of special interest to us are groups that have a finite number of elements in them, called finite groups. In order to measure these groups and use some arithmetical properties and properties of integers when talking about them, we want to give ourselves some definitions and terminology. So definition 28 says that the order of a group G with some operation star is simply the cardinality of G and is denoted with absolute value symbols around G. This is the same notation that's used in set theory to talk about the cardinality of a set, and because we're defining order as just the cardinality of the set, then it makes sense to use this notation. So we can apply this even when the group that we're looking at is not finite. So the cardinality of the group Z with addition is infinite, because there are infinitely many integers, and so the set Z that goes with the group G is infinite. So we say that the group Z with addition has infinite order. Let's look at the following. New group. Let's look at the set containing 1, -1, I, and -I, where I is the imaginary unit, where I squared equals -1, with multiplication, ordinary multiplication. It turns out that G is a group under multiplication. This is an easy exercise. And we also have that the order of G is, well, first of all, we denote it by order of G, and it's 4. So G is a group of order 4. We can also talk about the order of an element of a group, and we're going to see in a little bit that there's a good reason why we're using the same term for both of these ideas. The definition 29 says, let A be in G, where G is a group. The order of A is, first of all, it's denoted similarly. It's denoted using the absolute value bars around A, and it's the smallest positive integer such that A to the n is the identity. Here we're writing things multiplicatively, as is default for us. If we had an additive group, instead of writing A to the n, we would write NA equals E if G is additive. So it's the smallest number that where you can take that number of copies of A and combine them all together using the operation and get the identity. Now, often, no such number exists. If no such number exists, then we say that the order of A is infinity. We say that the element A has infinite order. So let's do some examples with calculating order of an element. So let's let G be the group Z mod 6Z with addition. Now we know that G has 6 elements in it: 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, and 5 bar. We looked at this last time. So in particular, we could write that the order of G is 6 because G contains 6 elements. Let's find the order of the element 4 bar. Now, because we're writing things additively, what we're going to write things down with repeated additions as 1 times 4, 2 times 4, 3 times 4, 4 times 4, etc. And we want to see what the first one of these elements are that's actually equal to the identity. So remember that the identity of G is the equivalence class of 0. You obviously have to know that before you can compute the order. So if we just take 4 itself, 1 times 4, one copy of 4, that does not equal the identity. 2 times 4 gives us 4 bar plus 4 bar, which is 8 bar, which is 2 bar, and in particular, that's not 0 bar. 3 times 4 bar is 4 bar plus 4 bar plus 4 bar is 12 bar, which actually is equal to 0 bar. So this means that 3 is the smallest number, the smallest positive integer, such that 3 times 4 is equal to 0. So that means that the order of 4 in this group is 3. Now, as we look further, we can see that you'll find that 6 times 4 is also equal to the equivalence class of 0. So 6 times 4 is also the identity. When an element has finite order, then in fact their multiples or their powers are going to equal the identity an infinite number of times, over and over and over again, but the order is always defined as the smallest such number. Okay, let's look at another example. Let's see one using multiplicative notation. So now, let's let G be the set Z mod 9Z cross with multiplication. So G is the set of all elements that are equivalence classes of numbers modulo 9, but where the representatives are relatively prime to 9. So we get 1, 2, 4, 5, 7, and 8 as the elements of G. So once again, for instance, the order of G is 6, and we can look at the order of any one of these elements. Again, let's look at the order of 2 bar. Well, 2 bar to the first power is just 2 bar. 2 bar squared is 2 bar times 2 bar, which is 4 bar. And neither of these are equal to 1 bar, which is the identity of this group. 2 bar cubed. When you start getting up here into higher powers, it's often a good idea to split things up the following way, where you can use some of what you've calculated already to help yourself out. So I already know from the previous line that 2 bar squared is equal to 4 bar, and 2 bar to the first is just 2 bar. So we get 8 bar, which again is not the identity. And we continue. 2 bar to the fourth is equal to 2 bar cubed times 2 bar to the first. That's 8 bar times 2 bar to the first, which is 16 bar. Now 16 is congruent to 7 mod 9. And in particular, that means that this is not the identity. So we keep going. 2 bar to the fifth is going to be 2 bar to the fourth times 2 bar to the first. And when we get here, 2 bar to the fourth, I'm going to go ahead and use the simplest simplification of that. So 2 bar to the fourth is equal to 7 bar. So we get 7 bar times 2 bar is 14 bar, which equals 5 bar, which again is not equal to the identity. 2 bar to the sixth is 2 bar to the fifth times 2 bar to the first. Now 2 bar to the fifth is 5. 2 bar to the first is 2. And so we get 10 bar, which actually is equal to the identity. So in this problem, we had to go quite a bit further. And in fact, that we got that the order of 2 bar is equal to 6. Now, as you might imagine, the order of an element and the order of the group that it sits in when the group is finite are related to one another. In this case, you'll notice that the order of 2 bar in this set was 6, which is the same as the order of the group. That's going to tell us some things about it, but we're going to wait until a later talk to really explore that, because it turns out there's some very deep connections there that we want to make sure that we treat correctly. Another advantage that finite groups have is that we can actually write down a multiplication table for them, which can help us to understand them and to classify them. And we have a special name for this. So definition 30. Let's let G star be a set with operation. We aren't going to assume that G is a group here, because what we're about to construct applies to any set with any operation and can in fact be used to help prove that G is a group. The Cayley table, named after the mathematician Cayley, the Cayley table for G star is a matrix with entries in G and rows and columns indexed by the elements of G, where the element in row A and column B, where A and B come from the group G, from the set G, is A star B. Of course, an example is the best way to see what's going on here. So let's look at our set G from before. 1, -1, I, -I with multiplication. Let's see what the Cayley table for this looks like. So what we want to do is we want to write down all the elements of G along the top of the table and down along the left side of the table. And so then what we get in each spot of the table is the product of the element on the left with the element on top. Now this particular group is going to wind up being abelian, and so the order doesn't matter, but we'll do another example in a second where the order does matter. So in the column 1 and 1, we're just going to get 1. 1 times negative 1 is negative 1. 1 times I is I. 1 times negative I is negative I, and so forth. I times 1 is 1. I times negative 1 is negative I. I times I is negative 1. And I times negative 1 is 1. Negative I times 1 is negative I. We get positive I. Negative I times I is 1. And negative I times negative I is negative 1. So we can check a few things from this table. First of all, we can make sure that the operation that we're working with takes elements of G to elements of G, that we can make sure that G is closed under this operation by making sure that all of the elements that show up in the table are elements of G to begin with, which they are in this case. We can also try to identify identities. So an identity element has that its row and column are the same as the guide row and column. So, for instance, we can look at the element 1 and notice that its row in the table is equal to the guide row, the row at the very top. It exactly matches up. And that same element's column exactly matches with the guide column at the left of the table. And so when that happens, that means that the element that you're looking at, in this case 1, is an identity for the group that you were, or for the set that you are looking at with its operation. Once you do that, you have inverses. What you do is you make sure that the identity appears in each row and column. So the identity is 1, and so we can note where the identity occurs in the table. And to make sure that everything has an inverse, you want to make sure that the identity appears in every row and every column of your Cayley table. And if it does, then that means that your set with operations satisfies the existence of inverses. Now, the one thing the Cayley table doesn't do for us is prove associativity. Associativity is often a bit of a pain to check. The Cayley table can help us to do that because it lets us keep track of computations if we're having to prove associativity by hand, by just computing all the different combinations, which is not what you want to do, but happens occasionally. But once you know associativity, the Cayley table helps you to check all the other conditions for being a group. So in order to see where this fails, let's look at a Cayley table for something that we already know isn't a group, and we'll see how it fails. So let's look at the set G, which is Z mod, let me do Z mod 4Z with multiplication. We could also do Z mod 6Z, but I want a slightly smaller set here. So we're looking at multiplication now. Now the elements of G are 0, 1, 2, and 3 bar. And now we want to multiply them together and get the multiplication table for this set with the operation of multiplication. So 0 bar times anything is 0 bar. 1 bar times anything is that thing back. 2 bar times 2 is 4 bar, which is 0. 2 bar times 3 bar is 6 bar, which is 2 bar. 3 times 2 is 6, which is also 2 bar. And 3 times 3 is 9, which is 1 bar. So we can check via this table, is there an identity? And the answer is yes. If we look at this row, we see that it perfectly matches the top row, the guide row. And the second column exactly matches the guide column on the left. So this tells us that 1 bar is in fact an identity for this set with this operation. Well, then we ask for inverses. And so we go through and we note in the table all the places where we have where the identity appears. And we can see that we do not always have inverses. And that's because there are some rows and or some columns which don't contain the identity. So in particular, column 1 doesn't contain the identity, column 2 doesn't, and then rows 1 and 3 don't. I'm sorry, column 3 also doesn't include it. And this lets you know which elements of your set don't have inverses. They are the ones that correspond to these rows or columns that don't contain the identity in it. So the Cayley table can be used both to show that a set is a group under an operation, or that it's not a group under some operation. So finally, I want to talk about a class of groups that are easy to understand from the point of view of geometry. Let Dn be the set of symmetries of a regular n-gon. And what that means is that it's going to be the set of all the ways that you can flip or rotate a regular n-gon around so that it lies on itself, but where you've changed, you may have changed some of the locations of the vertices, even though the object lies on itself. For a particular example, let's look at D3, the symmetries of an equilateral triangle. All right, so I can look at an equilateral triangle here, and I can ask, what are its symmetries? What are all the ways of rotating or reflecting this shape so that it lies on itself, but some of the vertices may have changed position. So let's think about some of these. So one symmetry of the triangle, one way of moving it around, is to just not do anything with it. And we're going to call that the identity. So let's let 1 be the identity symmetry. That is with no movement. Let's let R stand for clockwise rotation by 120 degrees. So the point is that if you apply the rotation R to A, B, C, and you apply R to it, you're going to get a triangle again, but now all of the vertices have changed position. They've all rotated once around the circle or once around the triangle clockwise. Of course, we could go the other direction. Also, R prime is counterclockwise rotation by 120 degrees. So that would be another symmetry of the triangle, another way that you can move the triangle around to lie on itself by changing the vertices. And then we have three reflections. I'm going to let MA stand for reflection along the axis containing A. So reflection along this axis, which will keep A the same, but will switch the locations of B and C. And similarly, we can define the mirroring along B and the mirroring along C using similar reflections. And these are all of the symmetries of an equilateral triangle. And we can consider them as elements with an operation between them, where the operation is doing one of these and then the other. So if I compose any two symmetries, then I'm going to get a new symmetry out of it. So the composition of symmetries is a symmetry. So I want to use this as an operation. So, for instance, let's suppose that I want to reflect around the line of symmetry containing the vertex A, and then rotate clockwise by 120 degrees. Now, just like when we do composition of functions, I'm going to write that sequence from right to left. So this means apply the mirror transformation through A first, and then apply R. So to figure out what that does, let's just apply both of them. If I apply the mirror symmetry through A, that's going to keep A the same, but it's going to switch the locations of B and C from where they were originally. And now if I apply a rotation clockwise by 120 degrees, A is going to move to the lower right, C is going to move to the lower left, and B is going to move on top. Now what you'll notice is that if I look at just the movement from the original triangle to the final triangle over here, that is also a symmetry. This is the mirror symmetry through C. This is what I get when I reflect along the line of symmetry that contains the vertex C. So what we get is that R times MA is equal to MC. So if we apply mirror along the line containing A and then rotation R, then we get the mirror reflection along the line containing C. So we can Do this a bunch of times and develop the Cayley table for D3. Now, D3 has 6 elements. It has 1 R, R prime, MA, MB, MC, 1 R, R prime, MA, MB, and MC. So we just worked out that if I take R times MA, then that gives me MC. And by going through the same process, we can work out the rest of them. Now, the identity rotation or symmetry is really easy because it doesn't actually do anything. It just keeps everything the same. Also, to keep everything in line here, I'm just going to give myself a couple of guides here so that it's easy to tell what's going on with what. If I reflect along the same line of symmetry twice, I'm just going to get back what I started with. If I do MA and then MA, I get back the identity, MB and then MB, I get back the identity, MC and MC, I get back the identity, and so forth. Now, looking in the upper left quadrant here, if I rotate twice clockwise by 120 degrees, that's the same as rotating to the left clockwise by 120 degrees once. So R times R is R prime. R times R prime is the identity, because if I rotate clockwise by counterclockwise by 120 and then clockwise by 120, I get back where I started. And then if I rotate counterclockwise twice by 120, that's the same as rotating clockwise once by 120. Then we did R times MA is MC. Then if you go through the same process here, you'll get that R times MB is MA, R times MC is MB, R prime times MA is MB, R prime times MB is MC, and R prime times MC is MA. Just going through all this process. All right, and then we have MA times R is MB, MA times R prime is MC, MB times R is MC, and I am definitely just reading this off of something that I prepared before, because actually constructing all of this is time consuming, though none of it is more difficult than what we've already done. We get MA, MA, and MB here. And then finally, if we do two reflections that aren't the same, it turns out that gives us a rotation. So to see how that goes, let's take MA, MB. So we get A, B, C, like we had before. So if we apply MB, that's going to give us the triangle that looks like this. C at the top, AB on the bottom. And then if we apply MA to this, that means that we're going through the line that contains A, which is going to give us A, and then BC. And notice that if we move from the first to the last, this is just counterclockwise rotation by 120 degrees, or R prime. So MA times MB is R prime, and we get R, and filling out the rest of the grid, we get R, R prime, and R. If you want before we get into analyzing this, I will say that a very good exercise for working with Cayley tables is to work out the Cayley table for D4. Now D4 has 3 different rotations, because we could we rotate by 90 degrees, or clockwise or counterclockwise by 90 degrees, or we rotate the whole thing by 120 degrees, or 180 degrees rather. And then the lines of symmetry that you have look like this. So some of them go through vertices and some don't. So it may take you may have to work a little bit to make sure that you have everything notated correctly, but if you do so carefully, then you'll be able to write down the Cayley table for D4 as well. All right, we're not going to check associativity here, but we are going to check to see whether this set with operation has an identity and has inverses. For identity, we want to look for a row that exactly matches the guide row, and we see that this row does that. And a column which exactly matches the guide column, and the first column does that, and so we conclude that the rotation 1 is the identity. And once we've identified the identity, we want to circle or note in some way all of the identity elements in the Cayley table and make sure that every row and every column has an identity element. And as we look through here, we see that it does. Every row and column has an identity element, and so we have that inverses exist. Thus, D3 here is a group. The same is true for any Dn. These are known as the dihedral groups, and they form a collection of groups that are reasonably easy to understand, at least at first, because they have such visual representation.